Let's start with section 6.6, the matrix of linear transformation. So here's the first question. Find the matrix T from base P to base C of the linear transformation T from V to W with respect to the base B and C. So that means they're telling you B is on the vector space V and W from the space C from the space W. And here's the transformation from P1 to P1 defined by B minus AX to the base B and C. So, and here is the vector B, which is P of X, 3 plus 4X. So first of all, we need to find the matrix transformation, the matrix T from B to C. So we're gonna base on this theorem. They're telling you was this theorem. Let V and W be a finite dimensional vector space with base B and C respectively, where B is V1 until Vn. If the transformation V to W is a linear transformation, then the matrix n times n matrix as defined A is going to be the coordinate vector of V1 to the base C, the coordinate vector V2 to the base C, and keep going. And then it satisfies that A times V with respect to the base B is going to be the transformation of V with respect to the equal to the transformation of V with respect to the base C. So that's what we're gonna work on. So the first thing here is our basis B equals C equal 1 and X. And our vector is P over X equals 3 plus 4X. Then transformation of V is going to be transformation of this vector V is going to be 3 plus 4X. That means this is the A and here is the B. So here is the A and here is the B. So I'm gonna do the transformation. It says B minus AX. That means 4 minus 3X. That means it's going to be the vector 4 and negative 3. To find the matrix T from B to C, we compute the value of T with the base element of base B. So T with the base of element of B. The first coordinate here, because the base B equal 1 and X. And the same thing, the base C equal 1 and X. So don't confuse yourself because you have the same base from B. Down versatile A, which is 1 equal as a linear combination from the base B, which is 1 and X. So 1 is going to be 0 minus X. That means 0 and negative 1. And transformation of the X is going to be 1 minus 0X, which is 1, 0. So it looks like here what we're doing, you find in the transformation, take the base, here is 1, right? Find the transformation for the 1. The transformation of 1 is going to be 0 minus, because 1 is the A, so minus 1x. Then 0 minus 1x equal, we need to write down the coordinate factor, so I'm gonna write down a linear combination from the base C, so C1 plus C2 times X. That's mean. In this case, C1 is going to be 0 and C2 is going to be equal negative 1. That's why we got the vector 0 and negative 1. We're going to do the same thing with the X. So find the transformation for the X. The transformation for the X is going to be 1 minus 0x. Because here's the A. The A is 0 and the B is X, which is 1x. Write down the transformation is going to be 1 plus 0x. And write down this as a linear combination from the base C. So C1 times X plus C2, C1 times 1 and C2 plus X plus C2X. Then in this case, C1 is going to be equal 1 and C2 is going to be equal 0. That's why we got 1, 0. That means the matrix, the transformation from B transformation matrix from B to C is going to be C transformation of 1 with the base C and transformation of X with the base C, and here is going to be 0, -1, and 1, 0. So now A times the vector B with respect to the base B, which is the vector B with respect to the base B here, the vector B with respect to the base is going to be, just here is the vector, A is 3 and B is 4. So here is the vector B, and A times the vector B is going to be, here is the matrix, we multiply with the vector B is going to be 4, -3, which is the same thing, the transformation of B with respect to the base C, which is here. So we got this one equal the transformation of B with respect to the base C. That's why we proved the theorem by we get two equal sides. So let's check our solutions. We got it right. Let's move to the second example. I'm gonna do the second examples in details, and let's check what we're going to get. So the next example, we have the transformation from P2 to P2, the polynomial with degree 2, polynomial with degree 2, to find by the transformation of the polynomial P of X is going to be Px plus 2. That means each X value, because polynomial with degree 2 is going to be A plus Bx plus Bx squared. Now I'm going to plug in instead of each X, X plus 2. Our base B equal 1x squared, and our base C is going to be 1x plus 2, x plus 2 cubed. So let's x plus 2 squared, not cubed. So let's check here. Our vector B is going to be equal P of X, which is A plus Bx plus Cx squared. That means going to be A, B, C as a vector. The transformation of the vector B is going to be transformation of A plus Bx plus Cx squared, and the transformation for Px, we're going to put instead of each x is going to be x plus 2. So it's going to be A plus B, x plus 2 plus C, x plus 2 squared. Now here is our first part. Now let's mean with the base C. So this is the transformation of B with respect to the base C. Now to find the matrix T from B to C, we compute the value of T on each base element of B. The first element of B equal 1. The transformation of 1 is going to be 1 because we don't have x, so I can't plug in x plus 2 because it's just a number, the constant 1. Now I'm going to write down the 1 as a linear combination from the base C. So it's going to be C1 times 1 plus C2, x plus 2 plus. Okay, C1 is going to be equal 1, C2, because there is no term here with x plus 2, that means it's 0. C3, there is no term here with x plus 2 squared, that means equals 0. So our first column with the matrix from B to C is going to be 1, 0, 0. Now let's take the second element from the base B. C of X is going to be C of X, which is x, so I'm going to plug in x plus 2. That means x plus 2 is going to be C1 times the first vector, C2 times the second, C3 times the third one. This element is equal x plus 2. That means C1 is going to be 0, C2 is going to be equal 1, and C3 is from B to C is going to be 1, 0, 1, 0. Now, the third element, x squared, is going to be transformation of x squared, which is going to be x plus 2 squared. So x plus 2 squared equals C1 times 1, C2 times x plus 2 plus C3 times x plus 2 squared. And in this case, C1 is going to be 0, C2 is going to be 0, and C3 is going to be 1. So the third column is going to be, for the matrix, is going to be 0, 0, 1. That means our matrix from from B to C is going to be 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. The vector V with respect to the B is going to be A plus BX plus CX squared, which is ABC. That means if you multiply the matrix times the vector V with respect to the base, the vector V with respect to the base V is going to be the same thing, ABC. That transformation of B to the respect C here is, that's what we found here, which is the same thing if you write down as a vector is going to be A, B, C. That's where we got these two equal sides. So we satisfy the theorem 6.26. That's it for the second question. Let's check that. We got it right. Let's move to the third one. We're going to do exactly the same steps. So number 3, we have transformation from R2 to R3. Yes, R2 to R3, and defined by the transformation of AB is going to be A plus 2B, negative A and B, and we have the vector V, negative 11 and 11, and here is the base B, 1, 2, and 5, negative 1, and the base C, 1, 0, 0, 1, 1, 0, and 1, 1, 1. Okay, that's good. Just checking the numbers. So the first thing, we're going to find the transformation of V with respect to the base C. That means I'm going to plug in. Here's our vector V. So it's going to be negative 11 plus 2 times 11. So it's going to be 22 minus 11, 11. And the next one is going to be negative A. So it's going to be negative is going to be 11. And here is the third one, 11. So this is with respect to the base C. It's going to be 11, 11, 11. Next part, we're going to compute the coordinate vector of negative 11, 11 in B. That means we're going to find the scalars C1 and C2. So let C1 and C2 scalars such that negative 11, 11 is going to be with the in base B. So it's going to be C1, 1, 2 plus C2, 5, negative 1. Now let's find the scalars. We're going to solve the system. And then we're going to find the scalars 44 equal 11 C1. That means C1 is going to be 44 over 11. So C1 equals 4. Plug in 4 in the first equations. Move the 4 to the other side. So it's going to be negative 15 equals 5 C2. That means C2 is going to be negative 15 over 5 is going to be negative 3. Then negative 11, 11, the vector V with respect to the base B is going to be 4, negative 3. So this is the first part. Now, let's find the transformation of the vector with respect to the base C. The first vector with respect to the base C. So first of all, I need to find the transformation. So I'm going to plug in 1, 2 in our transformation here. So it's going to be 1 plus 2 times 2. So it's going to be 5. And the second vector is going to be negative 1. And the third vector is going to be 2. So now I'm going to write down, because I need to find the coordinate vector. So 5, negative 1, 2 as a linear combination from the base C, C1, C2, C3. You're going to get this system. 5 equals C1 plus C2 plus C3. Negative 1 equals 0 C1. So it's going to be C3 plus C2 plus C3. And 2 is going to be 0, 0 equals C3. That means C3 equals 2. So plug in 2 on the first equation, you're going to get C. I meant plug in C3 equals 2 here. So that means C2 is going to be negative 1 minus C3. C2 is going to be negative 1 minus 2. So C2 is going to be equal to negative 3. And I plug in negative 3 and 2 on the first equations to get C1 equals 6. So our first column for the base 1, 2, the first column from the base C, the transformation of 1, 2 with respect to the base C is going to be 6, negative 3, and 2. We're going to do the same thing with the second column, 5, and negative 1. So we're going to plug in 5, negative 1 here to find the transformation. and then I need to find the coordinate vector by write down the transformation of the linear combination from the base C. So we're going to do exactly the same steps. So the transformation of 5, -1 is going to be 5 plus 2 times -1 and -5 and -1. So it's going to be 3, -5 and -1. Now I'm going to write down the result as a linear combination from the base C. So we're going to get the system. By solving the system, we're going to get the transformation of 5, -1 with respect to the base C, 8, -4, and -1. Then the matrix of linear transformation from the base B to the base C is going to be T11, and the second column is going to be 5, and -1. So it's going to be the first column and the second column. So here is our matrix. We already know the transformation of V is going to be 11, 11, 11. Write down the 11 as a linear combination of the matrix of the base C. So the transformation of V with respect to the base C is going to be 0, 0, 0. So now we need to prove that. Here is the first part of the theorem. Now we need to prove that if I multiply the matrix A by the vector V with respect to the B, we already found the vector V with respect to the B, which is 4, -3. So if I multiply the matrix A by the vector V with respect to the base B, I have to get exactly the same transformation of T with respect for the base for the vector V with respect to the base C. So if you do this multiplication, it's going to be also 0, 0, 11. That's why we got this one equal A times the vector V with respect to the base B. So we prove that the theorem 6.226 is right by getting two equal sides. Let's check our solution. We got it right. Let's move to number 4. Number 4 is a little bit different. Let's check our solution for number 4. Number 4, we have the base e to the 9x. I think I get exactly the same thing. Find the matrix D with respect to the base B, which is e to the 9x, e to the 9x cosine x, e to the 9x sine x. And they're telling you the matrix D, it's mean the derivative. This is the derivative of the matrix, is not a base D. So that's the difference. So let's check here. And they're telling you you're going to use, this is on B, the condition B. So, okay, let's start with this one by finding the matrix. So A, so the matrix, the first column here with the base B is to the 9x is going to be equal. So here's the thing. So here's the first coordinate, here's the second one, and here's the third one. Keep in your mind, that means it's going to be 1, 0, 0. E 9x cosine x, this one is going to be the second one. So it's going to be 0, 1, 0. E 9x sine x, this one, the third one. So it's going to be 0, 0, 1. This is with respect to the base B. Now, the derivative to the first one, I'm going to work with the first one. The derivative of E 9x is going to be 9E 9x. Now, to write down the vector, so it's going to be 9, 0, 0, because it belongs to the first one. The derivative of the second one, so it's going to be the first function, the derivative of the first function, which is 9E 9x cosine x minus the second one times the e to the 9x times the derivative for cosine is negative sine. That's why we get negative e 9x sine x. Now write down as a column. So here we have e 9x cosine, which is mean the second one is going to be 9. The first one is 0 because I don't have like exactly like this term by itself. and we have like this term, so it's going to be -1. So here is the second column. The third column, we're going to find the derivative here. So the derivative is going to be the first one times the derivative sine x times the derivative for e 9x, so it's going to be 9e 9x sine x plus here e 9x, the derivative of sine is going to be cosine. So now it's going to be 0, 1, 9, because here is belongs to the third part, so it's going to be 9 here. This one belongs to the second one, so it's going to be 1 here, and we don't have e to the 9x, so the first one is going to be 0. So the matrix G with respect to the base B is going to be the first column 9, 0, 0, 0, 9, -1, and 0, 1, 9. So this is the first part. Now, to go to the next part, we'll do exactly the same thing what we did in example 1 and example 2. But keep in your mind, this is the type of your base. This looks like this is the first term, the second term, and the third term. So now our function of x equal four e to the 9x minus e to the 9x cosine x plus 9e 9x sine x. Because they give you this function here. They're telling you to start with 4, yes. Here is our x. Indirectly by using this method, and we're going to find directly by using the derivative, the regular derivative, and we're going to find the same two results. So f of x, now f of x with respect to the base b is going to be, here is the same function. That means it's going to be 4 as a first constant, and the second one is going to be -1, and the third one is going to be 9. The derivative of our function is going to be the matrix G times this one. So here's the matrix G times this one, so it's going to be 36, 0, 82. Now to write down as a function, because we already know our first constant is e 9x, the second one is e 9x cosine, and the third one is e 9x sine. That means 36 e 9x. The second one is going to be 0, so I don't have to write down the second term. The third one is going to be 82 e 9x sine x. So this is indirect way. Now, this is the first part. Now we need to prove that if we find the derivative for this function, we're going to get exactly the same result. So let's check that. So here's our function, 4e9x, e9x cosine, e9x sine. Find the derivative. The derivative here is going to be 36 e9x. The derivative here is going to be e9x, the first one times the derivative for the cosine negative sine, plus the second one times the derivative for the first one is going to be 9e9x. I keep the negative sign out. Plus, find the derivative here, so it's going to be the first one times the derivative for the second one, for the sine is going to be cosine, plus the second one times the derivative for the first one is going to be 981 e9x. Now let's combine here. Here is the first part, is going to be negative times negative positive, and here is going to be negative, and here is going to be positive, and here is going to be positive. So cancel these, that combine the back term, and here's 1 plus 81 is going to be 82. So we get exactly the same. This is the direct method, and the other one is indirect method. Let's check our solutions. You got it right. This is for number 4. Let's jump to number 5. Now, number 5, we're going to use the composition S composite with the T. So for number 5, we're going to use the theorem 6.27. Let U and V and W be a finite dimensional vector space with bases B, C, and D respectively. Let T transformation from U to V and S transformation from VW, then S composite with the T from the base B to the base D is going to be the matrix A from C, the matrix S from C to D, and the matrix T from B to C. So let's check that by using this theorem, and we're going to do example number 5. So we have transformation T, and here is S, and here's our bases. The base C and D similar to this one, 1x and x squared, and the base B is going to be 1 and x, because be careful, the transformation T from P polynomial with degree 1 to polynomial with degree 2, and the transformation S from polynomial degree 2 to polynomial degree 2. And here is our transformation S, and here is our transformation T. So here's all the information we need. Then the first thing we need to find S composite with T directly, and then computing its matrix. So let's check that directly. So here is our T and S. T polynomial with degree 2 is going to be A plus BX plus CX squared. So you're just gonna know this is the general form for polynomial with degree 2. Polynomial with degree 1 is going to be A plus BX. So here is our transformation T, and here is our transformation S, base, and here is the base C and the base D equal 1x x squared. Directly, S composite with the T to the BX, so S, and here's T to the BX. The transformation T to the BX is going to be PX plus 1. And be careful, from degree 1 to degree 2. So A plus BX. The transformation is going to be A plus B. I'm going to plug in, instead of X, it's going to be X plus 1. So X plus 1. So A, here is the A. B, here is the B. And instead of X, I need to plug in X plus 1. So it's going to be X plus 1. BX plus B. Now I have to write down this again, because here's a constant and here's a constant number. So it's going to be A plus B, and here's BX. Now to take the transformation S, this is A, and here is B. This is A, and here is B. So I'm going to do the same thing. I'm going to plug in, instead of X, I'm going to plug in X plus 1. So here is the first term, A plus B, and here is the second term, which is A plus B, X plus 1. Do the same thing, A plus B, convert this one, I'll distribute the B is going to be BX plus B. So in this case, B plus B is going to be 2B. So A plus 2B plus BX. So here's our transformation directly. Now, we're going to write down with respect to the base D. That means S composite with the T to the 1 is going to be S composite with the T 1 plus 0x, because the 1 is going to be 1 plus 0x. That means it's going to be 1, 0, 0. Now I need to write down as a linear combination from the base. So here is our polynomial with degree 2. A is 1, B is 0, C is 0. So find the transformation for this one, A. We don't have B and C. That means it's going to be 1. Plug in 1 here, 1 plus 2, 0 plus 0x. That's why we got 1 plus 0x. So we're going to get the vector 1, 0, 0. Write down the vector 1, 0, 0 as a linear combination from the base D. So the base D is going to be 1, 0, 0. The second one is going to be 0, 1, 0. The third one is going to be 0, 0, 1. As we plug in A, X, A, and here is BX, and here is CX squared, as here is the vector. Solve the system, you're going to get the transformation S composite with the T to the 1 with respect to the base D, it's going to be 1, 0, 0. You're going to do the same thing for the X. Now we have 0A plus B is 1. Plug in everything here in our transformation. So A is 0. B is 1, so it's going to be 2. B is 1, 2. The first one is going to be 2. The second one is going to be 1, because you're going to plug in 1 instead of the second term. And the third one is going to be 0. Write down this vector 2, 1, 0 as a linear combination from the base D. We got C1, C2, C3 is going to be 2, 1, 0. Because we have exactly the same base, so it's not going to do any change here. Transformation of S with respect to the T, S composite with the T from the base B to the base D is going to be 1, 0, 0, which is here, and 2, 1, 0. 2, 1, 0. So here is the first part. You're going to type everything here. Let me check it before we move into the next part. So I got this part is right. Let's go to the B. We're going to find the same thing by using theorem 6.27. And this is theorem 6.7, and that's what we need to prove. So we're going to find the matrix F from B to C, from C to D, and the transformation of the matrix T from B to C. And if you multiply these two matrices or two vectors, we don't know how it's going to be. You're going to get exactly the same matrix here. So this is the second part of this number. So I wrote everything, the same information here. But we're going to find using this theorem. So the transformation of 1, that means I'm going to find this one first, and then I'm going to find this one. For the first, with the base D is 1, the first constant. So 1, 0, 0. Write down as a linear combination from the base C. We're going to get C1 equal 1, C2 equals 0, and C3 equals 0. That means the first column of the matrix T is going to be 1, 0, 0. The second column is going to be X plus 1, because you're going to use the transformation. That means the first constant is going to be 1. The second one also is going to be 1. The third one is going to be 0. Write down as a linear combination, we're going to get C1 equal 1, C2 equal 1, and C3 equals 0. That means the second column is going to be 1, 1, 0. So the transformation T from base B to the base C is going to be 1, 0, 0 and 1, 1, 0. Now the transformation S from the base B, that means the base B is going to be 1. So it's going to be the same thing, 1, 0, 0. Write down as a linear combination, we're going to get 1 and C2, C3 equals 0. So the first column is going to be 1, 0, 0. And for the X, with respect to the base D, it's going to be X plus 1. So it's going to be 1, 0, 0. Write down the linear combination. We get C1, C2 equal 1, and C3 equals 0. So S to the X for the base, with respect to the base D, is going to be 1, 1, 1, 0. 1, 1, 0. Okay. For X, for S with X squared, you get the same thing. C1 equal 1, C2 equal 2, and C3 equal 1. So we're going to get for the S, X squared is going to be 1, 2, and 1. Now, next step, we're just going to multiply. That means our matrix from base B to the base D is going to be 1, 0, 0, 1, 1, 0, and 1, 2, 1. By using the theorem, if you multiply the base, the matrix transformation from B to C, and the matrix transformation from C to D, be careful, there are different bases. From B to C and from C to D. So that's why if from base B, the base B contains only 2 elements, which is 1 and X. From base B to the base C, so I contain 2 elements. But from base C to the base D, base C contains 1 and X squared, 3 elements. That's why we're going to get the 3 columns. So we're going to get 3 columns here and 2 columns here. Do the multiplication, we're going to get exactly the same thing what we got on number 8. And let's check our solution. We got it right. Let's move to number 7. Number 7, we're going to use another theorem. Let's check the theorem. Theorem 6.28, let T be the transformation from V to W, a linear transformation between n-dimensional vector space, V and W, and let B and C are bases, respectively. Then T is invertible. Invertible, that means there's an inverse. So this is really important. Invertible, that means there's an inverse, and that's what we need to find. If it's T is invertible, if and only if the transformation, the matrix T from B to C is invertible in case that means inverse is going to be the transformation inverse from C to B, and that's what we're going to use. So let's check example 7. We're going to do the same thing. We have a transformation from 2 times 2 to 2 times 2, and the transformation of A is going to be A times B, and here's the matrix B. First of all, we need to prove that T is a linear, the linear transformation T is invertible. So this is our first step. And we have the basis. Our basis is the standard base. T is invertible by considering its matrix with respect to the standard base. So our standard base, I'm going to say, here's my standard base, E11, E12, E21, E22. E11, here is the base, E12, and E respectively enter E22, which is 0, the standard base. That means the transformation of the first element on the standard base is going to be, I'm going to do the transformation. That means the matrix times B. So here's our matrix times the matrix B. So we're going to get 8300. That means the first column is going to be 8300. We're going to do the same thing. The transformation of the second element on the standard base. So the transformation is going to be A times B. That means here is the matrix, our matrix, times the matrix B. So we're going to get the third column, 3100. The same thing with the third element on the standard base and the fourth element on the standard base. We're going to get 4 columns. That means our transformation from G to the G, which is the standard base, is going to be, here's the 4th column. Now, until now, we didn't prove that. It's a theorem. That means that this matrix is invertible if and only if the determinant of this matrix not equal 0. So if you find the determinant for this matrix is going to be equal 1, that which is not equal 0, that means this transformation or the linear transformation are invertible. So the first part we're going to choose invertible. So all these steps just to find the matrix, and then we have to prove that the determinant is not equal 0. That means then the transformation is invertible. So now it's invertible. So we need to find the inverse. I have the matrix. To find the inverse, what we're going to do, we're just going to use Gauss-Jordan method to find the inverse. So here is the steps. Here is the matrix. Here is the identity matrix. By using the row operation, we're going to get, here is going to be the inverse. That means our inverse is going to be negative 1300, 3, negative 1, 0, 0, 0, 0, negative 1, 3, and 0, 0, 3, negative 8. So here is now our inverse. So now if you multiply the transformation by any vector with R for the matrix 2 times 2. So here is a matrix, because our matrix, if you say in general A, B, C, D, that means if I multiply our transformation matrix with A, B, C, D, I'm going to get negative A plus 3B, 3A minus 8B, negative C plus 3D, and 3C minus 8D. So now write down, this is the first element, this is the second one, this is the third one, this is the fourth one. So here is the inverse transformation for the matrix T. Here is the inverse one, the inverse transformation, which is going to go back from this side to this side, from the matrix 2 times 2 to the matrix 2 times 2. So here is the inverse transformation for the matrix T. Let's check our solution. We got I. Let's move to number 7. We're going to do exactly the same steps, what we did here on example 6. But now our transformation is different. Our transformation is A, B minus BA, and our B matrix. So the first thing we need to prove that it's a linear transformation. A linear transformation T is invertible. So here's our standard base. The transformation of E11 is going to be A, our matrix, times the matrix B, minus the matrix B times the matrix A. We got, this is the first column. We're going to do the same thing with the next column. The transformation of E12 is going to be the matrix A times B, because now this is look like the matrix A, and here's the matrix B. So I'm going to do the transformation. We're going to get the second column, and we're going to do the same thing with this third one and the fourth one. So we got the matrix T from the base G to the base G, which is here, the columns. Now, this matrix is invertible if the determinant not equal to the 0. If you find the determinant for this matrix is going to be equal to 0, that means that then the transformation is not invertible. I'm not going to move to the next step, which is going to choose this one. So we got it right. That means we can't prove the theorem because the linear transformation is not invertible. The last one, example 8, a linear transformation T from V to V is given possible. Find the base C for V such that the matrix T with respect to the base B of T with respect to the C, okay, is diagonal. Diagonal matrix, that means we're going to make connection with the diagonal matrix, which is the diagonal element is going to be the eigenvalue. So let's check that. So here's our information, diagonal matrix. So here's our transformation. So our transformation is just like 0A minus 8B. So I'm going to write down as a matrix. So here is my matrix. By theorem 6.29, let's check this theorem. Theorem 6.29, let B be a finite dimensional vector space with base B, and C, let T from B to V be a linear transformation. Then the transformation matrix with respect to the C is going to be P inverse T with respect to the B, P. So it's like diagonalizing matrix. So that means this matrix is going to be, the diagonal for this matrix is going to be the eigenvalue. And the rest is going to be zeros. Let's check this theorem. So that means I need to prove this one. This one is diagonal matrix. So the determinant for this matrix minus lambda I to find the eigenvalue is going to be equal to 0. So negative lambda, negative 8, 1, 6 minus lambda equals 0. So find the determinant for this matrix. So we found 2 lambdas, lambda equals 4, and lambda equals 2. So now we need to find the eigenvalue because I need to find the matrix P and then P inverse. P, I already know the matrix T is going to be 4 and 2. So it's going to be 4 and 2 and 0, 0. So we already have this side, but we need to prove this side. And when we multiply B inverse times the matrix T with respect to the B times the matrix P is going to be equal to the matrix T with respect to the C. So when lambda equals 4, plug in 4, we're going to get the eigenvalue, the eigenvectors. Solve the system. So the eigenvectors is going to be x1, x2 equal negative 2 and 1. So this is the first column of the matrix P. Now, when lambda equals 2, plug in 2, so it's going to be -2, -8, 1, 6, -2. Let me check. Yeah, negative lambda, okay. So -2, -8, 1, 4, because I need to find the eigenvectors. So we got the system, solve the system. So we got the eigenvectors, -4 and 1. That's mean we already know that T with respect to the C is going to be 4, 0, 0, 8. But I need to prove the other side. That means our matrix P is going to be the eigenvector 1, the eigenvector 2. So it's going to be -2, 1, -4, 1. The inverse for this matrix is going to be half, 2, -half, and -1. Now, T inverse transformation with matrix T with respect to the base P times P. T with respect to the B, here is the matrix. This is T with respect to the base P. Multiply by T, we're going to get the matrix 4, 0, 0, 2, which is equal the matrix T with respect to the base. Check our solution. Be careful. When you plug in here, you're going to plug in the matrix P. The matrix P, which is the eigenvalue from lambda 1 and the eigenvalue from lambda 2. That means this matrix, you're going to plug in this one here. That's it for section 6.6.